How's it going, everyone? Mr. Geyser here with the final video in our Lesson 11 series where we're taking a look at example 5 and example 6. For example 5 here, we're going to use the table of values below to determine whether the function is increasing or decreasing and the concavity of the function. We want to try and make a sketch of it, and can you determine the domain of these functions? For part A here, we're given these x and f of x values, where really we can just plot them onto this first graph right here, where we have that first point, that second point, that third point, and that fourth and fifth point are like way off the grid over there. So we just want to keep that in mind, that this graph as it increases is very steep, where it's like, or sorry, very, very flat. It's not steep. You basically increase it and it just teeters off to like a plateau. But really, it is still increasing. So for us here, we can describe that f of x is increasing at a decreasing rate because the rate of change is decreasing. It's concave down. It's pretty easy to see that this is concave down. And the domain looks to be 1 to positive infinity. I'm claiming it to be 1 here because it doesn't quite pass 1 in the lower end of the table. And in general, I know that these limits here are going to approach a number pretty quickly, but never cross that number. And since I can see that as we're increasing in our x exponentially, our f of x isn't really increasing all that much. So if we were to decrease exponentially, I don't think we're ever actually going to get close to past 1 there. If we take a look at g of x, or part B, we have these points here, where we're now able to plot them onto a graph in blue, where we're given these 4 points, with the 5th point being way off the graph here. We can plot this graph here. It's a little bit easier to see the steepness of it ending right up here, where we can describe g of x as it decreasing at an increasing rate because the rate of change is increasing. This f of x and g of x are very similar to example 3, where we took a look at those f of x and that negative g, or that negative f of x, where we have that same kind of decreasing at an increasing rate and increasing at a decreasing rate. For g of x here, it's concave up, with its domain to be looking around to be -2 to positive infinity, where it's not really crossing that -2 line in that x there. So we can kind of assume it's going to be right around -2. Now, let's take a look at example 6. In example 6 here, we'll be using this application in an investment kind of way, where you're given an initial principal P that's invested at a 6.25% interest rate that is compounded continuously. And as it increases by the amount of K times the original principal after T years, where T is equal to the natural log of K divided by that interest rate of 0.0625. In part A here, we're going to complete the table and determine how long it takes before your initial investment doubles. The doubling comes from the K amount, and the T comes from the amount of time it would take. So all we're doing is plugging in K into our equation here, and we end up getting this table here, where 0, or for 1 here, the initial amount is after 0 years. But we double our amount after 11.09 years. So the claim that I want to make is that it will take around 11 years, 11.090, to double the initial investment. Now let's take a look at B, where we're using our TI-84 calculators to graph this function on there. So we take out your TI-84 calculators. On this one here, I happen to clear it. All I really want to do is I want to hit y equals, and this is where I want to put in my t equals function, where I type in this parenthesis. I'm going to use ln parenthesis of x here, x you can find right there, close parenthesis, divide by 0.0625. Now we could do it this way here, but I want to show you how we can put this exact fraction into our calculators. For this here, if you want to keep it in that function form there, I'm totally okay with that. But if you want to be a little bit extra, clear your calculator out and hit this math function here. If you go into math and you tab over 1 page, you're given like absolute value, round, I part, F part, all that jazz. Just hit up on the page and you end up with this n divided by d, numerator divided by denominator. If you hit enter, you get a mini fraction inside of your calculator. And in that top part there, I want to put ln of x. In our case, we're going to use x instead of k, close parenthesis. I'm going to tab down to get 0.0625. Now this gives me the exact same function, it just looks a little bit cleaner. I'm now able to go to the graph right here and I see, oh, it's kind of hard to see, right? It's like really, really pushed over a bit. So let me change the window so it kind of matches the window that's described here. So to do that, I'm hitting Windows on my calculator. For my x minimum, I'm going to do like right around -5 here. I feel pretty good about -5, just a little bit past our y-axis. So -5. So I'm using that negative function down here, hitting 5. For that x maximum, I'm going to go a little bit past 20, 25. I'm going to keep that scale as 1. For my y minimum, I'm going to keep it at that -10. Kind of just goes down a little bit. But I'm going to go up until about 65, kind of spreading that out. I'm going to keep my, my intervals for my scale here the same. So y scale is 1, y minimum is -10, y maximum is like 65. Now when I hit graph, I end up getting this kind of graph on our calculators. This logarithmic graph, as time goes on, it takes longer and longer for us to double that initial investment. In part B, we want to just bring this graph down and try and copy it onto our graph here. Luckily for me, I have that snip tool, so I'm able just to copy it onto the graph right here. I want you guys to try your best with putting this graph onto your table here. Really just graphing these points onto our table. If we take a look at this final part here at C, C here states that suppose you have $1,000 and you invest with that function there the amount in the account at any time t, which would be for this formula A of t is equal to 1,000, that initial amount, times e raised to the power of 0.0625 times t. That's that inverse equation based on our k. We want to use this function here to verify that your answer, my claim that it will take about 11.09 years to double that amount. So what we're really doing is I want to prove this claim here mathematically, that this is the claim. It's going to take 11.09 years to double that $1,000. And all I need to do is I'm going to plug in to this equation that 11.09, so I get A of 11.09 equals 1,000 times E raised to the power of 0.0625 times 11.09, and I'm going to prove to you that you're going to get $2,000 exactly. Okay, I'm a little bit short. It's about 4 cents short, but it's like right around $2,000. Well, that's not precise enough. What I want to know from you for a bit of extra credit is what exact amount of years in as many decimal places as you can find would our investment actually be exactly, no more, no less, $2,000. For this here, we know we're going to be right around 11.090 something something years. And if you're clever, you can find that amount with some inverse function. You'll have to find it somewhere in part C. You could plug and chug, but I want to see if any clever students can find that answer. Thank you very much for joining me for these 3 videos for our Lesson 11. I look forward to seeing all of you guys in class. Take care.